way out. So we are going to finish talking about gerrymandering this week, and then we'll move on to something completely different. Actually, this is the end of our sort of democracy-related topics. The rest of the class will be about something completely different. But anyway, we were talking at the end last time about the convex hull ratio. So I want to continue talking about that. The convex hull ratio. This is, remember, it is a specific mathematical measure of how weird the shape is. So for instance, something like this shape, say, this one is somewhat weird according to the convex hull ratio. Remember, the way that you measure the convex hull ratio is you have some kind of original shape, and then first of all you figure out what is the convex hull of that shape. And this is the shape you get by adding straight lines to fill in any of the kind of inward facing innies in the shape. All right, another way to think about it is if you were to wrap a rubber band around the shape, what is the rubber band encircle? In this example, you get basically all of this stuff is unchanged, but this inward facing lump gets filled in the convex hull. So remember, you always do this using straight lines. It would look something like that, and then this amount gets filled in, and of course the entire rest of it. So the original shape there is like with the white inside, and then the bigger shape with the red inside is called the convex hull of the original shape, right? It's fairly easy to draw the convex hull if I give you a shape. And the convex hull ratio is a specific number, which I usually write as CH, the convex hull ratio. And the definition is it's the area of the original shape divided by the area of the convex hull. Right? This is what I said at the very end last time. The convex hull ratio is the area of the original shape divided by the area of the convex hull. Now, because the convex hull is always bigger than what you started with, it could be equal or bigger, it's never smaller. That means that this is always a fraction where the denominator is going to be bigger than the numerator. So this actually always gives you a number between 0 and 1. It's a fraction where the denominator is bigger, so it's a like when you write as a decimal, it's between 0 and 1. So this CH is a number between 0 and 1. And this number sometimes is written as a percentage for that reason, but when it's close to 1, I'll say a nice looking shape has the convex hull ratio close to 1. That's because a nice looking shape is already convex or pretty close to being convex, whereas a weird sort of squiggly wormy shape has a convex hull ratio closer to 0. So a weird shape has the convex hull ratio close to 0. All right? And you can use this to measure exactly how weird the shape is. That's the point of this measurement. All right? Remember, the idea here is that this can be used to evaluate a weird gerrymandered map, and as a specific way of measuring how weird the shapes are, because generally a very weird looking shape is evidence that somebody is trying to mess around with your maps to gain an advantage. All right? The major problem with doing this in the real world, so what I would like to do today is I have a stack of handouts here, including the 5 different districts in the state of Connecticut for Congress, and I would like us to try to calculate how weird the shapes are in this particular sense, the convex hull ratio, the area of the original district divided by the area of the convex hull. The problem with this in a practical sense, how would you actually compute these numbers on a real map? The issue is areas of weird shapes are hard to find, right? Like when you're in high school, everybody learns like how to find the area of a rectangle or a triangle or even a circle, that kind of thing. But just like a weird shape like this one that I drew right here, anybody know the formula for a shape that looks like this? The answer is no, there isn't really a formula for that. It's just a weird like bean shape. Areas of weird shapes are hard to find. So how are you going to actually find the area of a shape that I give you on the homework or whatever? In the real world, the districts in Connecticut, like those 5 districts, they do have areas that like somebody knows, I guess, how many acres are in District 1 or whatever. But this is difficult to do. There's actually a tool for this, though. A tool for measuring areas. I don't know if you remember, I gave a talk last week about some instruments for measuring areas of weird shapes and distances of weird curves. One of them is something that I talked about in that talk. This is a tool for measuring areas. This is like, I know it's early in the day, this is likely the stupidest thing you've ever heard of today. It's a very, very sort of dumb idea, but it works really very well. It's called the dot planimeter. This word planimeter is a fancy word for like area measuring tool. There are other kinds of sophisticated area measuring tools, but the dot planimeter is very, very unsophisticated, and I have a little handout. Basically what it is imagine you have a weird shape just like drawn on your paper and you want to find the area of that shape. A classical dot planimeter would be some sort of transparent sheet that you lay on top of your shape, and it has a bunch of dots on it, equally spaced dots. And all you got to do is like count the dots that are inside your shape. Here, you'll see what I mean. I have a very simple, if you feel like this is a very simple and stupid idea, you are right. But it works really well, actually. Any one of us could have come up with this idea. The dots. All right. So this is the fabulous dot planimeter. I'm going to try to get this on my screen too. All right, so the idea here is finding the area of a weird shape is hard. You don't have formulas to find the area of like Connecticut District 2 because it's not a normal geometric shape. So how do you find the area? Let's say I want to find the area of this heart. The idea is you make this grid of dots, and each dot is separated by, say, 1 centimeter or whatever. You can use whatever units you want, all right? And then all you do is you count up how many dots are inside your shape. And that's how big the area is, right? If that sounds like a dumb idea, it's a simple idea, but it works pretty well. I mean, it's not exactly accurate. Can I say, why does this work to get the area of the shape? You have to imagine each of these dots is really like the center of a little square. And if the dots are 1 centimeter apart, these squares are each 1 square centimeter. So when I'm counting the dots on the inside, really it's the same as counting how many of these little boxes fit in the shape. Now some of the boxes stretch out past the shape, so you get a little too much area on some of the boxes, but actually some of them are undercounting because here's a little bit of area which was not under any of the boxes. Anyway, you get a little bit of overestimations, a little bit of underestimations, but if you do it with enough dots, these overestimations and underestimations, you expect them to more or less even out, and you end up with a fairly accurate reading for what the true area of the shape is. So like for instance, right here, if I was trying to find the area using the dot planimeter, you just count how many dots are inside the shape. And it's helpful if you have a pencil or something to like mark them off as you count them. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And so this shape is about 16 square centimeters, or whatever the units are. Yes? Yes, what about if it's on the line? This is a big question which will come to your mind, which I want to talk about in a moment. If you scroll down on the page, you'll see that's a topic to discuss. But this is the basic idea. She's getting ahead of me. Any questions about the basic usage of the dot planimeter? As far as I can tell, I actually did a little research on the origins of the dot planimeter, and it seems to have become a thing like like around the 1920s, which in my opinion is a lot later. I would have expected this to have been invented far earlier than that because it's such a simple idea. But I think it's a matter of the technology. Before the 20th century, it would have been difficult to make these things. Like I said, this is usually done with a transparent sheet with dots printed on it. And it was not easy to make transparent sheets before the 20th century. You could use this with glass and then somehow paint dots on glass, but maybe that's more trouble than it's worth. Anyway, by the early 20th century, this became so cheap and easy to do that it was actually a very commonly used technique in science in the 20th century. I know this was a big, I don't know if you guys are into this, but this was a big deal in measuring the area of leaves, like tree leaves. People studying how healthy their trees were, they wanted to measure the average area of the leaves, and they used the dots to do it. All right, so this is the dot planimeter. This is how we are going to measure the area of our weird shapes when it comes to measuring gerrymanders. It's not perfectly accurate, but it is actually pretty close. If you're doing this in the real world and you want really good accuracy, you would scale the dots really small. That makes it more accurate, and you could also lay down your sheet several times and like take the average of your readings, but we don't want to get into that. All right, what about if the dot is on the line? You will notice that I failed to count certain dots because I judge them to be, certainly if the dot is outside, then you don't count it. But what if it's right on the line? These ones I judge to be kind of on the line, but still outside. Although there's one here which is on the line. Maybe it looks like it's still inside. Here's another one on the line. If you think about it, what a dot on the line represents in terms of the areas of the little boxes, like for instance this dot on the line, it sort of represents the fact that like half of this box should be counted, right? A dot on the line is like a half a box worth of area. And so when you're counting up the dots, really the most correct way to do it is to count. If the dot is on the line, you count it as a half. Now this is a pain to keep track of, and so there's a little trick, which you can see at the bottom of the paper here. You make two different types of dots, and rather than counting halves, which is a pain to keep track of while you're counting, these two different types of dots, the difference only matters when it's on the line, but I said here, so if the dot isn't on the line, you just count it no matter what. So all the ones that are definitely inside, you definitely count. If it's on the line and it looks like this, you count it. If it's on the line and it looks like that, you don't count it. So if you do it in this way, the effect is you end up counting about half of the ones that are on the line, which is what you want to do if each dot on the line represents a half. All right, so this is, in this way, if I'm counting here, I would count all the ones that are on the inside first. Now this has a slightly different positioning of the dots than before. Those are all the ones that are inside. I guess that one looks like it's inside also. But then when it comes to the ones on the line, you only count the ones that look like this on the line. And if this one is on the line, you don't count it. The whole point of this is so that I'm only counting about half of the ones on the line. So I will count this one. I will not count these ones here. I do count this one, this one, this one. And that's about it. All right, so this one, count it because it's on the line and it has that shape to it. Whereas this one here is also on the line, but it's the other kind. Don't count it. Sorry, I'm scrolled off the bottom there. All right. The point of the two different types of dots is just to help you when it's on the line to only count half of them. And the rule is if it's the if it's the one that looks like that, you do count it. If it's the one that looks like the other one, you don't count it. And actually it doesn't, if you find yourself forgetting which is the one I'm supposed to count and which is the other one, it doesn't matter. You just do it one way or the other. The whole purpose is that you're only counting half of the ones on the line. All right, any questions about that? This is the fabulous dot planimeter. It's a totally simple idea, but super useful actually. Deceptively stupid as an idea. All right, sometimes that's the way it works in mathematics. You know, sometimes the best ideas in math are very, very complicated, but oftentimes the best ideas are like the simplest, stupidest, most obvious ones. Okay, this is how we are going to measure the convex hull ratio. Really, the purpose of the dots is just to find the areas, which is not easy if it's a weird shape. Okay, let's try. I got some examples to try. Here's a handout. What I have on the paper here are the 5 state of Connecticut congressional districts with the dots so that you will be able to count the dots. I hope you don't mind counting the dots. It's a little tedious to count them up, but it works. All right, so I would like for us to compute the convex hull ratio of each of these shapes. Maybe I'll do 2, and then I'll have you guys try the rest of them. So I'm going to get this file also. Dots. These are the real Connecticut districts. Now, some of these, just to print them all on the paper, I scaled them up and down. In real life, some of them are bigger than others. And I also, just for fun, I put the whole state on there too. Of course, the whole state is a lot bigger than each of the individual districts. But it doesn't matter how you scale them up and down. And actually, the units of the dots don't matter. I printed out these dots not in any particular, like they're not actually separated by 1 centimeter or whatever. They're just in a regular arrangement. It doesn't matter. So anyway, let's try to find the convex hull ratio of District 1. Remember what it is. It's the original area. So this is, I'm going to do number 1 here. All right, it's the convex hull ratio is the original area divided by the area of the convex hull, right? So first I will count up the original area. What you got to do is count the dots, and I'm going to mark them off with my pencil, and I'm going to count them out loud, which will mess you up if you're counting them in your head right now. Sorry to do that. And remember, the ones which look like, so I'm going to, when it's on the line, I'm going to count this kind. Count this one if on the line, right? And I'm going to skip this one if on the line. If it's on the inside, you count them both, no matter what. This difference between the 2 different dots is only when it's on the line that matters. Okay, so here I go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Whoa. 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. I got 27. Anybody agree? Now, if you counted this up and you got like 26 or 28 because maybe you thought 1 was outside that I called on the line, that's fine. If you're like when you're doing this on the homework or whatever, if your answers are off by 1 or something, it doesn't matter really, because you're gonna make this fraction and then divide it, and you'll end up with something the same as my answer anyway. What did I say? 27? I should have wrote it down when I think I said 27. Is that right? Yes? Okay, thank you. Somebody said yes, that's right, 27. All right, that's the original area. Now I need to count up the area of the convex hull. So I hope you all remember how to, first of all, draw the convex hull. It involves making straight lines, and I'll try and draw the convex hull on top of this picture, let's say in blue. What you got to do is connect that part to fill in, I'm not going to scribble it in just because that will make the picture look all messy, but you definitely have to connect up this part here to fill in this much. So all of these dots now, they were not originally included in the shape, but they will be included when I count up the convex hull area. And then to make it convex, I need to go across the bottom like that. I also need to go up the side, fill in all the innies, all right? The effect is the new region, the blue outline, is going to surround more dots than I had before, all right? Anyway, I think the blue outline now is where the convex hull goes. And then I'm going to count the dots that are inside the convex hull. Now, I said hell, convex hull. Feels like hell when you're counting the dots. It's hot in here too, isn't it? Yeah. Sorry about that. I've been meaning to call someone about that. I haven't yet, sorry. I'm hot too. Let's count the dots now which are inside the blue. Now, I already marked off the red ones there, so I'm going to actually just start from 27 and now count up the additional dots that I picked up inside the convex hull. All right, maybe instead of crossing the new ones out, maybe I'll circle them just so that I can tell. So I was at 27 before. Now I go 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41 is what I get. Anybody agree or disagree? I got 41 dots inside the convex hull. You will so I'm going to write that down so I don't forget. You will notice right here is a dot on the line of the convex hull, but that's the kind of dot that I don't count when it's on the line, so I did not count that one. Otherwise, there was not a real issue about things being on the line or not. All right, this is how we do it. Any questions about that? So my final answer is 21 over 47. Now, if this was on a test or something, you just leave your answer like that. Just for the sake of comparison, I divided this on my calculator. I believe this is about 66%, I think. I don't know if those are exactly the same numbers that I got. But if you have, anyone have a calculator? Can you tell me what you get for that?
66.
66, all right. You get something like 0.66, whatever, I rounded it. All right, so even if your counts are like off by 1 or 2 from how I counted, this number will end up being more or less the same as what I got, as long as you're doing it correctly. All right, let's do together, let's try the whole state just for fun, and then I'll have you guys try out the other ones, and I'll walk around and make sure you're doing it all right. Okay, so the whole state, same deal. I'm going to count the dots which are inside the original state, including ones that are on the line, if they look like this. So I'm going to count that one. These other ones I'll say, these ones look like they're inside too. I'll count those 3. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I got 41 inside. Anybody agree or disagree? If you got something like 41, then you're probably right. There's a few ones that are like, if it's really close to the line, it's a little debatable. I will leave it up to your discretion to call it if it's close. Actually, I think this one, I should have counted this one too. So I'm going to say 42, whatever. And then the convex hull. I have to add in some straight lines. Say there, and then probably all the way across the bottom of the state. Also a little bit there. And this little notch up there. Do you ever see that? There's like a little bite taken out of the state on top. This little thing here. Any Northern Connecticuters out there? Is there a name for that little thing? Somehow Massachusetts like stole a town from Connecticut at some point in the deep past. I don't know much about it. Somewhere, there must be people angry about that. But anyway, I will count up the new dots. So starting at 42, which was my original count, plus an additional. I think these ones are on the line now. So I'm going to say 43, 44, 45, 46, 47, 48, 49, 50, 51. I'm going with 51. All right. Can someone do those numbers for me? It's like 80, 81%, something like that. 82%, 84%, 82. All right. If I say enough numbers, one of them will be right. 80. Come on now. Sorry, my pen. 82%. Okay, great. So I hope that everybody is clear on this. That means, in the sense of the convex hull ratio, the shape of the whole state is actually better than the shape of District 1, right? District 1 is like 66% good. The whole state overall is 82% good, which is gooder than the District 1. Okay? I would like you to try the other ones with our goal, let's try and like rank the districts about which one's the best, which one's the worst in terms of the convex hull ratio. Try them out, and then we'll move on to something different. It's probably best if you count in your head for the sake of your neighbors. If you have a little calculator, do the numbers just so you can compare one with another. Okay?
Okay, I switched. Okay.
Dots will not get back. Those are right.
Let's take a couple more minutes and then we'll go on to something else. Thank you for your patience counting the dots. You know, yeah, I'll tell you. All right, can we talk about these? I know not everybody's done, but I mean, after a certain point, you get tired of counting the dots over and over again. So I don't want to make us do this all day long. But I'll tell you the answers that I got at least. And your answers should not be exactly the same as mine, but they should be like vaguely similar. One thing that should be exactly the same as mine is how you draw the convex hull, right? You got to make sure that your lines are actually going in the proper places. Like, for instance, this line right here, I saw some people only connected it like down that way, but it really has to go all the way out here to avoid any kind of any regions. And same with, well, there are lots of places around the picture in which if you draw the convex hull the wrong way, you will get the wrong area when you are trying to count up the dots. But anyway, when I did measurements, maybe I'll just write them on the... So my answers, which like I say may differ very slightly from yours, and that's fine. For number 1, I got 66%. For number 2, I got 81%. Yeah. For number 3, I got 69%. For number 4, I got 66 again. And for number 5, I got 76%. So if your answers are slightly different from mine, that's fine. If they're like very different, then it probably means you drew your convex hull wrong and you missed some parts. Yeah. In terms of like when I'm grading these,
Yeah.
I don't know. If you're like 1 or 2% different, then that's probably fine. If you're like 10% different, then probably you did it wrong. Or I suppose maybe I did it wrong. All right. I mean, if I'm grading this on the homework or on the test, I'm not just going to look at your number at the end. I'll look at your pictures and whatever. So I should be able to tell if you're doing it right or not. Yeah.
And would 79 for number 5 be okay?
Yeah, probably. If you got 79 and I got 76, I mean, maybe I messed it up. It's just like counting the dots. I'm not any better at it than you are. But yeah, I mean, check to make sure that your shape is like mine. But yeah, if it is, it's probably fine. All right, great. This is all that I wanted to say about the convex hull ratio. Okay, so in those terms, it seems like according to the convex hull ratio, District 2 is kind of like the best shape or the least weird shape. And that actually, if I'm just looking at these sort of informally, if I just take a glance, District 2 actually does look like a fairly ordinary shape. It's more or less a rectangle with a weird little thing up there, I guess. Whereas District 1 looks quite weird, just like at a glance. And 5 looks pretty weird too. So yeah, number 2 is the best. Number 1 and number 4 are the worst in terms of this particular measurement. Number 4 is where we are. All right. Any thoughts about that? It's a little. I don't know how this corresponds to your intuition. Like I said, when I look like at a glance, to me it looks like 1 and 5 are the weirdest. Although 5 has a better convex hull score than 4 does. So the particular measurement of the convex hull ratio is not always exactly match sort of your intuition. I think the reason that 5 looks weird, but it's not so bad in terms of the convex hull, is like this little guy here is very weird looking, but when you look in terms of the dots, actually it only makes a difference for like 1 dot. So that actually doesn't have much of an effect, even though it's a weird looking thing on the shape. All right. Any further questions about the convex hull ratio? It's fairly simple to do. If you have the dots, you just count up the dots. In the real world, they do this by actually computing the real areas, which if you're using a computer, it's easy to find the area of a weird shape using a computer. But you know, for our purposes, just for the sake of being able to do it on the homework and on the test, counting the dots works pretty well. All right. That's the end of our discussion of the convex hull ratio. I have one more geometric measure of how weird a shape is. And this one has a fancier sounding name. This is called the Isoperimetric quotient. Quotient, you know, means like when you divide things. This is also a ratio. It's a fraction that you get at the end. And it can also be read as a percentage. So this is just another way of measuring how weird the shape is, but it has nothing to do with the convex hull. It is also about areas, but the isoperimetric quotient is, well, let me just draw some pictures here. So this is a not so weird shape, right? According to the convex hull ratio, or this other one, the isoperimetric quotient. Here is a shape which is weird, something like this. All right. S for my name. It's my favorite letter. It has to be. I met a kid this weekend. I did a trunk or treat this weekend, and I made a giant life-size Wordle board that you can like put letters on. And I got a lot of little kids who were like, yeah, I want to play that. But they're like in kindergarten or something. Like I knew they could definitely not play the Wordle. And I asked one kid, I thought this was funny. I said like, you got to be good at spelling to do this game. Are you really good at spelling? she's like, oh yeah, I'm great at spelling. I'm pretty sure this kid doesn't know how to read. So I said, all right, well, you gotta start with you gotta guess a 5-letter word. So what's your favorite 5-letter word? She said. She thought about it for a moment and then said, H. I thought that was funny. I think her mom came over and it went fine. Really, my target audience was really the moms, not the kids. I was very popular. There was like a little gang of beer moms, a bunch of moms carrying with beers. They loved it. That's my demographic, I guess. So anyway, the isoperimetric quotient. They may not love me sober, but with the beers, they're into it. This is about areas, but it's also the other hint about this. It's also here you can see right in there. It's about areas and also perimeters. All right. So according to the isoperimetric quotient, what we're looking for here, which will identify the second shape as weird, is that the second shape has a lot of perimeter and not a lot of area. Whereas the first shape has kind of a lot of area and I suppose not so much perimeter, right? Remember, the perimeter is the distance around the edge. Okay, so I'm going to say the one on the left is not so weird because this has sort of big area, small or I suppose not so big perimeter. Whereas the one on the right, this has small area, big perimeter. All right, so the isoperimetric quotient, I'm going to write IQ for this, is all about the relationship between the area versus the perimeter. If the perimeter is too big, then the shape is too weird. That's the idea behind the isoperimetric quotient. All right, so the IQ is a measure of area versus perimeter. And it's basically, this is not the formula, but this is the initial idea. It's basically just the area divided by the perimeter. If you do this and the perimeter is super big, then this fraction will be close to 0. And if the perimeter is not so big, then this fraction will be a lot bigger. That's the idea. The area divided by the perimeter. Now, there are some issues. So that is not actually the formula for the isoperimetric quotient. And it's because this formula, can I just write like A divided by P? So I'm going to use A for the area, P for the perimeter. That's not the formula we're going to use because there's a problem with that. This simple version of the formula, I will say this is okay, but doesn't scale properly. For example, if I try to do this with, say, a unit square, which is 1 inch or whatever on the side, then any masters of geometry out there, what's the area of a square with 1 unit on the side? The answer is 1. You do. I hope you remember. The area of a rectangle is you multiply the width times the height, and it's 1 times 1 in this case, right? Because it's a square. So the area is 1, and what's the perimeter? That's the distance around. It is 4. All right. Yeah, I'm not trying to say anything too fancy. Okay, so that fraction, A over P, would be 1/4. All right? Fine. What about, though, what if I consider a square that's 10 on each side? All right? Now, this is the same shape. It's bigger, but it's still the same shape. I would like for the answer to be the same because the isoperimetric quotient is meant to be a property which measures the shape, not how big it is or how small it is, but just what the shape is. It's a square. Okay, so this one, though, in this case, the A would be 100 because the area of a rectangle, you multiply the width times the height. The perimeter, what's the perimeter here? 40. And so now when I divide, I get A divided by P would be 100 over 40, which is 10 over 4. This is like 2.5, right? These are totally different answers, all right? That's the problem with just doing A divided by P. You get the number does not scale properly. If you use the same shape but measured at a different scale, it changes the answer. And this is regarded as a bad thing because I want something which is only a measurement of what shape it is, not how big it is, all right? So instead of, I will just say, it turns out we need to use, instead of A over P squared fixes all those problems. I would say like an informal reason why this is more appropriate is because the area is a two-dimensional measurement. Like the units of area would be like square inches or square centimeters or something. Whereas the perimeter is a one-dimensional measurement, and it's not really appropriate to divide like square inches divided by inches. When you're dividing things, they should have the same units. And it turns out, if you square the perimeter, then everything works out great. So in the previous examples here, if a square has 1, the area is 1, the perimeter is 4, and if I go A over P squared, I get 1 over 16. And if I do the same thing with the bigger one, here the A was 100, the P was 40, and here I would do A over P squared, this time is 100 over 1600, and I get 1, this is the same as 1 over 16. All right, I'm trying to say these now are equal to each other as they should be. So if you square the P, then this formula works properly at different scales. And so this now, actually, this still is not quite the formula. So the real formula, we'll use this, 4 pi A over P squared. All right, this is the formula for the isoperimetric quotient that, unfortunately, you'll have to memorize this. I said on the first day of class, there are no formulas that you're going to have to memorize, except one. This is the one. This is the formula, which you'll have to memorize when we do it on our test or something. 4 pi A over P squared. It's basically A over P squared, but it has this extra 4 pi. What's the point of the 4 pi? The 4 pi is there so that a circle has isoperimetric quotient equal to 1. If you do the geometry using a circle, you should always get 1 as the answer, and this formula was specifically designed to give you 1 if you're using a circle. That's the point of the 4 pi. If you're using a circle, the perimeter will be something like pi times the diameter, and this 4 pi is meant to cancel out the perimeter, the pi's that you get from the perimeter. All right, the 4 pi is there so that a circle has isoperimetric quotient of 1. Okay. Can I just tell you a little bit about the isoperimetric quotient? So this is what, in mathematics, we call it the isoperimetric quotient, and it has that formula. When this is used in politics, when people are talking about the shapes of gerrymanders or whatever, in politics, they don't call it the isoperimetric quotient. It has somebody's name. This is called the, has kind of a cute name, I guess, the Poulsby-Popper score. This is what they call it if you read articles about measuring gerrymandering. In that context, they call it the Poulsby-Popper score. This measurement has been used often, like throughout history in the sciences. It first appeared, as far as I can tell, this first used, this is a little weird, in a 1927 paper on paleontology, that is like dinosaur bones. Apparently, paleontologists care a lot about like digging dirt, and this isoperimetric quotient was invented as a way to describe how round individual grains of sand are. So apparently, like some places you dig, the sand is very round, and some places it's like got weird shapes to it. And they used this isoperimetric quotient to describe shapes of grains of sand, which I guess paleontologists care about. Anyway, it's used to measure how weird a shape is. All right. So let me just say, the isoperimetric quotient is always between 0 and 1, just like the convex hull score. That means you can write it as a percentage, right? It's always between 0 and 1. And close to 1 is good. That would indicate a nice looking shape. Specifically with the isoperimetric quotient, close to 1 means that it's close to a circle. Because in terms of the IQ, the circle is regarded as like the perfect shape. It has the circle has isoperimetric quotient 1. Everything else is a little bit less than 1. So close to 1 is good, which is close to a circle, and then close to 0 is bad. This would indicate some sort of super wormy shape, which has a lot of perimeter and not much area. All right, like a worm. Lots of perimeter, not a lot of area. This is actually a more commonly used measure in politics, more common than the convex hull score for whatever reason. I'm not sure why they like this one better generally, but nationwide, so the U.S. Congress districts average isoperimetric quotient is 0.23, just to give you an idea of what these figures generally look like in the real world. So the convex hull score is generally a lot closer to 1 than the isoperimetric quotient. A convex hull score of 0.23 is very hard to get. That would be very, very low for the convex hull. Like you saw in our examples, it's like in the 60s, 70s usually. But the isoperimetric quotient typically reads much lower, because districts are not typically going to be like circles, right? They're like weird shapes. The worst one, sort of the record, is the state of Maryland. District number 2 has the isoperimetric quotient equal 0.02. This is very, very low. This is the record for the worst. And if you look at this shape, it looks like an insane kind of wormy shape to it. All right, I got some examples for us to try. Again, I'm going to try one, and I'll have you guys try the others. Now, the problem with this one is you have to measure the perimeter, right? You can measure the area using the dots, but the perimeter is another issue entirely. And in fact, so I will say this is a bit of bad news, maybe. There's no good way to measure perimeters on paper. You can measure the area with the dots, the dot planimeter. Actually, there is an on-paper instrument similar to the dot planimeter, which is for measuring perimeters of shapes, but it's a little weird and I didn't really want to get into it. So we are going to do some examples that are just on grids like this. And the grids, you can find the perimeter very easily on a grid. So we're going to confine ourselves to examples like that for the isoperimetric quotient. A lot of handouts today. All right. So let's try Oops. What? Added it in a weird spot. Oh no. Something weird happened. It's all right. Okay, let's try the first one. I don't know if you're holding it properly. Turn it around so that this one is first. All right. You might have to turn it around. Let's find the isoperimetric quotient of that. So to find the area on the grid, you just count up how many of the dots there are. All right. So maybe I'll say, give me a new page, buddy. New page. I think maybe I have to write on this page. Yeah. So for the area, just count the squares. All right. If your shape is on a grid, then to find the area, all you got to do is count up the squares. And then for the perimeter, you count up the distance around the shape. So let's try this one right here. For the area, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 23 dots in the area. When you're doing these ones, you should really get exactly the same answer that I do if you do it right. So here, the area is 23. And what about the perimeter? Now, this is the distance around the outer edge. So I have to count, and I will maybe do it like this. I'm going to start in the upper left corner and go around, sort of snake around the edge and count the perimeter that way. I count like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, I got 36 around the outer edge. I hope that you also got 36. Anybody agree or disagree? I hope you agree. All right. And so for the first shape, the isoperimetric quotient, I'll write it up here, is 4 pi times 23 divided by 36 squared. And that's how I would expect you to leave it on a quiz or a test. You really can't go any farther than that without a calculator. All right. 4 pi times 23 over 36 squared. If you like, for the sake of comparing this with the other ones, you can plug that into your calculator. Maybe I'll find my calculator here. I said, what'd I say? 4 pi times 23 divided by 36 squared. 0.223 is what I got. So this is 0.22, or 22% if you like. All right? That's how we do the isoperimetric quotient. All right, in our remaining 15 minutes, can you try the other ones? And we'll see how it goes. 13 and 20 when I did that first one there. I hope you did too.
So you do 1, 2, 50. So you would do the ones that are connected. It's on the outside of the shape, like yeah, it's not like this. To here, to here, here. Everything that's like on this first spot that's exposed to the count. So you count 1, 2, 3, 4, 6, and for this body to split this, and then you wouldn't count this one, you just count this one. So it only goes on one side. You don't have to do this, you just plug it in there. These are the three other two. So just Yep. Yep.
Can we chat about these? I think once you get the hang of it, there's not much to it. You just got to be sure to do it right. So the first one here, the upper right corner, I got 13 for the area and then 20 for the perimeter. That is, you're counting the distance around the edge of these shapes. And if you plug that into the formula, you get 4 pi times 13 divided by 20 squared, which on my calculator I got 40%. You gotta be a little careful on your calculator when you're typing these in. Make sure you have to square the denominator before you divide, usually, the order of operations. Yes? No, I might ask you to put it into your calculator on the homework. Say I might give you two shapes and say like which one has the better isoperimetric quotient. In that case, you need to calculate it like if you want to compare the answers between two of them, because if you don't put it in your calculator, it's hard to tell which of those is bigger, right? But on a test or something, I will not ask you to calculate it because you're not using the calculator. All right, for this one here, a straight line here, I got this, 7 for the area, 16 for the perimeter. Did anybody plug this one into your calculator? No, I'll do it. 8%? Anybody agree or disagree? That actually sounds right to me. This is interesting here. I want to actually say something about that. 0.08 as a decimal, or 8%. I'll write it as 0.08. Anyway, for this one here, I got 11 and 24 for the area and the perimeter. I hope that you all agree. And then for these, I didn't get that far, but these should be similar. Anybody want to tell me, what did you get for the area for this one? 14? Anyone agree? Yes? And the perimeter? 20. Other people seem to be agreeing. I'm just writing this down so that everybody else will see the answers if you want. And how about for this one in the lower right? 21 area and the perimeter? What did you get? 32? 32. All right, they seem to say 32. Okay, great. Let me just say, we got 6 minutes remaining. I would like to make a comment about this right here, all right? This is a long and skinny rectangle. So the IQ for a shape like this is actually quite small. Right? That one, when we did it, was like 8%, right? Around 8%. I would like to compare this with what is the convex hull ratio for the same shape. Remember, this equals the area of the original divided by area of the convex hull. All right. Anyone want to say, what would that be in this example? Yeah. It would be 1. Yeah, why do you say that?
Because it's in this shape. You wouldn't have to fill in the convex.
Yeah, because the convex hull here, like this shape already is convex. The convex hull is the same shape. It has no additional area, right?
Why is it 1 not 0? How do you get?
Yeah, it's 1 because the area of the original shape is equal to the area of the convex hull. And so this fraction here equals 1. That's because these areas are equal in this case. All right, so can I just say a long, skinny rectangle, like myself, has a great convex hull score, but very bad isoperimetric quotient score. All right, so when you are, these are two different ways of measuring how nice the shape is, but they really mean different things. The convex hull ratio means how nice it is in terms of being convex or not. And the isoperimetric quotient means how nice is it in terms of being a circle versus being a skinny, wormy thing. And the long, skinny rectangle is regarded as bad with respect to this measurement, but good with respect to this measurement. It's because they're measuring two different things. So when you're doing this in the real world, you kind of have to decide what you care about in the real world, and measure what you care about rather than measuring something else. All right, and I think that'll do it. This is the end of gerrymandering. So next time, be prepared for a fresh start.